Hi, I'm Clive. This video introduces a small app that I've written that explains the basics of Newton's three laws of motion. It tries to explain why the laws are given in the order that they are given, and also takes it a little bit further to the idea of the normal contact force and also the relationship between the contact force when an object is resting on a surface like the ground or the table, and its relationship to the weight of the object, because the normal contact force, Newton's third law, and equilibrium can easily be confused, and approaching the laws in the order that they're given and understanding what they say, what they mean, and also what they don't mean helps you draw a more accurate force diagram, which is fundamental to solving these kind of mechanics questions. The link to the app is given below. Also, there's a link to the contact details. So if you want to ask me a question about this video or about a related subject, you can send me a message. I hope you find the video and the app useful. You navigate to the app from the standard URL. The URL is also given below. Let's look at the basic ideas within Newton's three laws of motion. Selecting mechanics and then Newton's laws of motion. Most people who have studied any mathematics and certainly mechanics will heard of the idea that there are three laws of motion. They're basically an attempt to describe the motion of objects as a result of forces acting on the objects. There are three laws. The first law, otherwise known as the law of inertia. The second law, which deals with force and acceleration. The third law about action and reaction. And then I've added another tab on contact forces, or the normal reaction force, because this can be misunderstood, and its relation to the third law is very important in creating correct force diagrams and then correct equations to solve a problem when two or more objects are in contact with each other. Looking at the first law, it grows out of the idea that prior to Newton, and probably prior to Galileo, the underlying idea was that for an object to move and to continue to move, it needed to be pushed. And that was stated by Aristotle and other philosophers of antiquity. Newton changed that model by saying that objects continue to move unless a force acted on them, which caused the object to change its motion. So the first problem to be addressed is, on the Earth, when we push an object, quite quickly it comes to a stop. Now, why is that? Because when the force is removed, an object stops moving. And why is that? We have to introduce another force, the friction force, between the object and the surface it's in contact with, that's trying to resist or oppose the motion of the object. The second law then relates force to a change in momentum, or more simply, if the object's mass is fixed, the force applied is proportional to acceleration. Simply, if you push an object harder, then it accelerates more. Then the question is, what do we mean by acceleration? And the acceleration is some change in the motion of an object, either or both the speed of the object, it speeds up or slows down, or a change in direction of the motion of an object. Now relate this back to the first law. If an object isn't being pushed by an overall external force, then it will continue to move in a straight line with unchanging speed, that is, with constant velocity. If an object's motion changes, its direction of motion changes, or it speeds up or slows down, the explanation for that in Newton's model is that a force has been applied to the object. So have a go at the worked example, and then as you answer each question, click on the Reveal Equations button and see if your argument is the same as the one given in the application. There's a small historical background, especially the contribution that Galileo's investigations did to changing the idea that an object needed to be pushed continuously to keep moving, to the idea that an external force causes an object to change its direction of motion. Galileo did this by rolling objects down an inclined plane and performing some measurements on those. Then there's a bit more historical background about characters who are maybe less well known in this area, but still made extremely important contributions, especially Simon Stevin and René Descartes and Christian Huygens. Johannes Kepler in his study of the motion of planets, which Newton then did further work on to explain Kepler's observations. Then Newton's great rival, Hooke, and the dispute over the idea of a central force and the inverse square law. And then there's a summary about the generally accepted explanation of the contribution of these various characters and how Newton used their contributions to come up with his 3 laws of motion. And the third law is often stated a bit simply as for every action there is an equal and opposite reaction. But to be a bit clearer about what that means, I feel it would be better to say if an object A exerts a force on object B, then object B exerts an equal and opposite force on object A. Properties of that are the forces are equal in magnitude, they're opposite in direction, very importantly they're the same type of force, and they act on different objects, each object acting on the others. And then there's some examples of the effect of charge and the forces it generates between 2 objects which are relatively close to each other, whether the charges, the electrical charges, are the same or different. Another example is when an object with mass m is released from above the Earth, and recognizing that as a result of Newton's third law, that both the Earth exerts a force on the object, a gravitational force, to pull it towards the Earth, but at the same time, though normally ignored, the object is pulling on the Earth. But the difference in the measured behaviour is down to the vast difference between the mass of the object and the mass of the Earth. Separately, there's a section on contact forces and where they come from, and recognising that the contact force is actually a Newton 3 pair, but the contact force is independent from gravity. However, there are lots of circumstances where we have objects resting on the ground, and we need to understand how to correctly draw the force diagram as a result of the contact force and gravity acting on the object, which is not a Newton 3 pair acting on the object, because the forces are of different type. They come as a result of different causes, gravity and contact, and they're both acting on one object. However, there are Newton 3 pairs in this situation, and this bit of text explains what they are. Hopefully that clarifies the 3 Newton's laws of motion and how to use those ideas in correctly drawing your force diagrams when working on a mechanics question.